All right, so now that we have taken the time to understand what things like curl and divergence mean, we can really start to dig into what do all of these Maxwell's equations actually mean. One of the amazing things about Maxwell's equations is that these four equations describe all of electromagnetics. And by taking the divergence and the curl of these four different vector quantities, you can describe any electromagnetics system. The four vector quantities are 1, d, the electric flux density, b, the magnetic flux density, h, the magnetic field intensity, and e, the electric field intensity. Hey, Milan, what's up? How are you? Are you sad? What? Why are you sad? What's going on? Oh, really? Seriously? You mean it in the last video there were 210 views but only 7 likes? Oh my goodness. Well, Milan, it's okay. I mean, it doesn't mean just because people don't like the video doesn't mean they don't like you. I promise. These other two quantities, rho v and j in Maxwell's equations, are the charge density, and we'll talk more about that, in coulombs per meters cubed, and j is a current density in amps per meter squared. Another thing I want to mention is that D and E and B and H are actually very interrelated. They both represent electric and magnetic fields, but epsilon and mu are constants of proportionality that tell you about the material properties of the problem that you're working with. And we will definitely delve into more details on this. To help us understand Maxwell's equations, it's really helpful to start off with some more simple problems or special cases of Maxwell's equations. The simplest case is when you have electrical charges that are not moving or they are stationary, and we call this whole field electrostatics. If that is the case, our Maxwell's equations simplify. So what ends up happening is if your charges are stationary, your current density is going to be 0 because they're not moving. So that goes to 0. Also, your electric fields, because all the charges are stationary, they're not going to be changing with respect to time. So this partial derivative will also go to 0. In the same way, because everything's stationary, nothing's varying with time, the derivative of b with respect to t is also going to be equal to 0. So what this is saying is that when it comes to the magnetic field, the divergence of b is 0, and the curl of h, or the curl of b as well, because b and h are proportional, is equal to 0. When you have a field where the divergence and the curl is equal to 0, mathematically, that means that the actual vector field is equal to 0. So that basically, the electrostatics will reduce down to 2 equations here. The divergence of D is equal to the charge density, rho v, and the curl of the electric field is equal to 0. I want to make a brief comment on how this result has an intuition behind it. First, it's saying that the divergence of the electric field is equal to the charge density, and it's saying that the curl of the electric field is equal to 0. This makes sense because if you remember, the electric field from a point charge is directed radially outward from the point charge. There's nothing circulating about that electric field. It's all just flowing out from the point charge. And if you're dealing with electrostatics, it's basically a summation of a bunch of different point charges that have radially outgoing electric fields. So if they're radially going outward, it makes sense that you would have some kind of divergence of the electric field. But the curl though, because it's just a summation of all these different electric fields that are flowing out from point charges, there's no circulation of the field. And so therefore everywhere the curl of the electric field will be zero. So hopefully that just gives you a little bit of an intuition of how that works. This first equation of Maxwell's equations, the divergence of D is equal to rho V, is called Gauss's law, and it is the fundamental equation that governs electrostatics. Before we talk more about Gauss's law, I first want to backtrack a little bit and talk about some of the principles we've been using in previous videos to help us explain what Gauss's law is and what it's really saying. So if you recall in previous videos, we've been making use of the principle of superposition, which says that if you have a collection of different charges and you want to know what is the electric field at a certain point in space, what you do is you sum up the electric fields from all the individual point charges. The electric field from each point charge is given by this, and this was derived experimentally through Coulomb's law. So this is how, in general, how you determine the electric field at any point in an electrostatics problem. One thing that we can do is we can take that general approach and we can generalize it with the concept of a charge distribution. So the process I showed you with having all these different point charges and adding up all their contributions, that will allow you to solve any electrostatics problem. And here what I'm about to show you is a method that's the same approach, but it's involving this concept of charge distributions. All right, so step one is, given any electrostatics problem, you break up the problem into a bunch of little cubes. The space, the different objects in the problem, break it up into a bunch of little tiny cubes, really infinitesimally small cubes. Secondly, you want to find out the net charge in each little cube. So in any given material, there's going to be electrons and protons, and normally they cancel each other out. But what you want to do is you want to look at each little cube and then find out how much net charge or excess charge is there. How much more electrons than protons is there, or how much more protons than electrons is there. And you do that for each little cube in the problem. We define the charge per little cube as the volumetric charge density. So that's the term there that was in your Maxwell's equation. So the charge per unit infinitesimal cube, that's the what we're talking about there when we talk about charge density. So once you know rho v, or the charge per meter squared, at every little point where you have a small cube, then what you do is you treat each little cube in your problem as a little point charge with a charge that's equal to rho v. Finally, the last step is to sum up or integrate all the fields from all these little cubes or little point charges to determine the total field at any point. And so that's essentially what we were doing in the previous slide, with just having the individual point charges and calculating that. But this sort of charge distribution way of looking at things is much more general, a much more general way of solving any kind of electrostatics problem, no matter how complex. So you can state this more generally. If you have some volume, we'll call it V prime, or some electrostatics problem, you break the volume up into a bunch of little cubes, find out the rho V associated with each little cube, and then if you know the distance, if you want to find the electric field at a certain point here, and you know the distance from each little tiny cube, you can integrate a differential electric field. We say that each little tiny cube represents a small differential electric field here at the point here. So if you integrate that, then you will get the total electric field. And this here, this equation here, that just comes from the original formula for the electric field from a point charge. But you're essentially integrating over the entire volume and treating each little infinitesimal volume as a point charge. And so this is a general method for solving any electromagnetics, or I'm sorry, any electrostatics problem. One thing I want to mention is that in addition to volumetric charge densities, sometimes in electrostatics we work with surface charge densities. So a surface charge would have units of coulombs per meter squared instead of coulombs per meter cubed. And in a similar manner, you can break up the surface charge into a little infinitesimal surface, which acts like a point charge, and then you can integrate over that to find the total field coming from a surface charge. A similar thing you can do actually with a line charge density as well. Sometimes you might have a line and you specify a certain number of coulombs per meter along that line. You can take a little dl or infinitesimal segment of that and treat that as a point charge and then integrate across the line to find what the electric field is at some point. So all of this, basically essentially the same principle, just in different formats. Okay, so here's something cool. All these integrals I'm showing you, the superposition stuff and breaking up the whole problem into cubes and everything, all of that whole process that you can use to solve any electrostatics problem can be conveniently summed up with this equation, Gauss's law. Now this might be counterintuitive that this simple equation could summarize that whole step-by-step process that I outlined, but my hope is to break this down so that this makes sense to you.